This lesson covers some material from Unit 3-4 using algebra. We're going to look at some stuff from Box B here, collecting like terms. And what we want to be able to do by the end of this lesson is identify what like terms are in expressions or in polynomials, and we want to be able to add or subtract like terms from each other. The easiest way to tell you what like terms are to give you some examples of things that are like terms and some things that are not like terms. So if we have something like 5x squared, this is a term, something like 7x squared, okay, would be a like term with it. So we could say that 5x squared and 7x squared are like terms. What is the definition of like terms? Well, like terms have the same variables. So in this case, we have x and x as our variable, and the same exponents on those variables. So here we've got an exponent of 2, we've got an exponent of 2. So these two things are like terms. The coefficient doesn't matter. It doesn't matter what number we have out in front there. As long as the variable part and the exponent are the same, these things are going to be like terms. Okay. So let's just take a look at some things that are like terms and are not like terms. Are these things like terms? Negative 3x and negative 4x. What do we think? Like terms or not like terms? They are like terms. Why are they like terms? What's the variable? So they both have the variable x. What is the exponent in each case? We don't see an exponent there, so what exponent do we assume is there? We assume that a 1 is there. So they have the same variable, they have the same exponent. Okay? Coefficient is different, negative 3 and negative 4. Doesn't matter, they're still like terms. What about the next pair here? Negative 3x and negative 3y. Like terms or not like terms? What do we think? Why not? Right. Don't have the same variable. So not like terms. Because one has an x, one has a y. Right, what about our next pair here? 7x and 7x squared. Like terms, not like terms. What do you think, Emily? Why not? Exponents are not the same, right? We've got a 2 here, and we've got a 1 there. Got to have the same exponent. Okay, 9xy squared and xy squared. What do we think? Like terms or not like terms? Now remember, these are terms because all of these things here are multiplied together, so they make one term. What do you think? Why are these like terms? Yep, we got variable x and y, so the variable parts are the same. We've got a 2 and a 2, and of course, a 1 and a 1 there. What about this next pair? 12xy squared, 12x squared y. Like terms or not like terms? What do you think? Who wants to give this one a try here? All right, go ahead, Stephanie. Right. Okay. They have the same variables, x, y, and xy, but here the x is to the power of 1. Here, the x is to the power of 2. So that 2 is kind of on the wrong exponent for them to be like terms. So this one here would have to be x squared y, or this one over here would have to be xy squared. Okay. Next one here. 4xy squared z, negative 5 zx y squared. Like terms or not like terms? What do you think, Andrew? You're right. These are like terms. How do you know, Andrew? Absolutely. Y has the same exponent. Bingo. It doesn't matter what order these things are in. Usually we write them in alphabetical order, but if they happen to be out of order, as long as the variables are the same and the exponents on the variables are the same, they are going to be like terms. What about 12 and 8 here? Do you think these are like terms? Now, first of all, what do we call 12 and 8 when we're talking about terms? What kind of terms are these? These are both constant terms. Are they like terms? What kind of a variable do you see on each of these? We don't see any variable. So they both don't have a variable. So do you think these are going to be like terms or not like terms? What do you think, Chris? It's actually the opposite. They are going to be like terms. Okay? Having no variable is the same as having the same variable. Okay? So whenever you see constant terms, all constant terms are like terms. And when I say they are like terms, I mean they're like terms with each other. Any constant is a like term with another constant term. Okay? Now, why are like terms important? Okay? It's helpful when we're working with terms here to try to visualize what these terms represent. So the textbook gets you to use algebra tiles and draw little pictures for a little bit. I wouldn't write this down. I would just sort of watch up here, and we'll take a look at how you can try visualizing these terms as we combine them together. What the textbook uses is it uses a tiny little square to represent 1. Okay? So if it wanted to represent the number 3, it would take 3 of these tiny little squares. Okay? It uses this long, thin tile, this long, thin rectangle to represent x. And it uses this big square to represent x squared, which is kind of easy to remember. X squared is the big square. So if we want to represent something like 2x, we're going to have 2 of these x's. If we want to represent something like 3x, we're going to have 3 of these x's. Okay? Now, are 2x and 3x like terms? Yes, yes, they're definitely like terms. And the way that you can visualize these as being like terms is, look at the shapes you have here. You have all the same shapes. All of these shapes are these long, thin rectangles. So all the shapes look like each other, so these are like terms. Now where we're going is we want to be able to add like terms together. So if I take 2x and 3x, and I add them together, 2x is here, 3x is here, what do you think these two things are going to add up to? Yeah, 5x. Because we are going to have, if we take these two and add these 3, we are going to end up with 5 in total. Okay? Similarly, if we're working with 5x squared and 2x squared, well, let's see. 5x squared is going to be 5 of these big squares. I don't think I'm going to have enough room to fit them all in here. I'll just put one on top of all the others. And I got 2x squareds down here. Again, are these like terms? Yes, because what you see are shapes that all look the same. Now, if I were to subtract these two, let's say, okay, I'm going to get rid of this. Cut. Cut. We're doing subtraction now. So imagine I've got 5x squareds, and I take away 2x squareds. I'm going to take away 2 of them. Well, that didn't work. Let's take away 2 of them. How many x squareds am I left with? Sorry, you guys can't see that very well. So if I started with 5, I took away 2x squareds, what am I left with? 3x squareds, right? Okay? This is the essence of adding and subtracting like terms. Okay? All right. Just an aside here. Why do we use the big square to represent x squared? Well, x squared has two sides. This side has length x, this side has length x, so its area is x times x, which is x squared. Okay. So imagine we have something like x plus 2x squared plus 3x plus x squared. Let's see, what do we have here? We've got an x. We add 2x squareds. Okay. We add 3x's. And then we add another x squared. I'm just going to rearrange these a little bit. I'm going to move this over here, and this over here, and this over here, and this over here like this. What do you think these two things are going to add up to if we add all of these things together? Well, how many x's do we have here, Abby? 4 x's. How many x squareds do we have, Felicity? 3. So we've got 4 x's and 3x squareds. Can we add these things and these things together? Well, no, we can't, because these are different animals, these are different creatures, these are different shapes. Okay? We can't combine, we can't say, oh, we have 7 whatevers. We have 7 tiles, but we don't have 7 x's. We don't have 7x squareds. We have 4 x's and we have 3x squareds. Okay? So that's what we're going to do when we collect like terms. Okay? So we can simplify. So this is probably what you want to write down here in your notes. We can simplify expressions by adding or subtracting like terms. And they have to be like terms. They have to be the same shape, okay? Same variable, same exponent, in order for us to add or subtract them together. And the rules that we're going to follow to add or subtract like terms is we are going to keep the variable part the same. Okay, so those x's are always going to be x's. We can't change those long rectangles into something else. And we're going to add or subtract the coefficients. So add or subtract those numbers out in front. So figure out, you know, if we have 4 x's and we bring in, well, we'll do one right here. We've got 3x plus 4 x's. If the variable here is going to stay the same, our variable still has to be an x. Our coefficients here are 3 and 4. 3 plus 4 equals 7. So that's going to give us our new coefficient, 7x squared. Okay? So if we have 3 x's, we bring in another 4 x's. How many x's do we have in total? We have 7 x's. Okay? So let's do some examples here. Okay. 2x squared minus 5x squared minus 7x. What we want to do first is we want to figure out, are there any terms in this thing that are like terms? So let's identify the like terms. What are our like terms here? Yeah, and I am just going to underline them, 2x squared, and I'm going to say that this term here is negative 5x squared. I'm going to imagine that that sign out in front of it stays with that term. So we've got 2x squared, and we've got negative 5x squared there. And then we got this negative 7x, which doesn't have anything that is like with it. Okay, so we've identified the like terms. Now we want to add and subtract the coefficients. So we're doing subtraction here. So if we've got 2x squared and we subtract 5x squared, we know that our variable is going to stay the same. We're still going to have an x squared. But what is the coefficient going to be on this x squared? Negative 3. Why is it negative 3? Because we're doing 2 minus 5 equals negative 3. So these integer rules that we practiced back in Unit 1 are going to come in handy here. What do we do with this negative 7x? It's still here. We can't forget about it, so we just write it as negative 7x on the end. So 2x squared minus 5x squared minus 7x is the same as negative 3x squared minus 7x. All right, let's do another one here. 4x plus 5 plus 7x plus 8. What terms in here are like terms? Always start with the like terms here. Stephanie. Okay, so we've got two sets of like terms. So I'm going to underline the 4x and the plus 7x. And I'll underline in another color the plus 5 and the plus 8. Okay. One thing that can be helpful while you're doing these is to move the like terms so that they're next to each other. So I'm going to move my terms so that my 4x and my 7x are next to each other. And when I move them, this sign that is in front of the term stays with that term. So this is going to be 4x and positive 7x. And then I'm going to have positive 5 and positive 8. Okay. And sometimes this just makes it a little easier to add your like terms together. All right, so now I've got my like terms right next to each other. If I've got 4x and I add a 7x to it, how many x's do I end up with? I end up with 11 x's. If I've got a 5 and I add an 8 to it, what do I end up with? A 13. So I add those like terms together. Can I add 11x and 13 together? Can I, Liam? Why not? Because they are not like terms, and we only add like terms. Excellent. Okay. So here's another one. 3a squared plus 2 minus 6a plus 3a minus 4a squared. Start by finding the like terms here. So what things in this are like terms? And let's just go from left to right. We got a 3a squared. Is there anything that is a like term with 3a squared? Yeah, negative 4a squared, because I want to get in the habit of thinking of that negative sign as going with that term there. What about my positive 2? Is there anything that is a like term with positive 2? Emerson, I see, he's shaking his head. He says no. Is there anything that is a like term with negative 6a here? And I'll do like a little squiggle there for negative 6a. Lexi. Positive 3a. Okay. So I found my like terms. I'm going to rearrange it so my like terms are next to each other. 3a squared minus 4a squared. Okay. I'm going to move my a's so they're next to each other. Negative 6a plus 3a. And then I'm going to put my positive 2 at the end. Okay. And now I can combine my like terms together. I can combine my a squared terms, my a terms, and I'm just going to be left with that 2 at the end. Okay. So 3a squared minus 4a squared. What are we going to end up with when we do that? 3 minus 4 gives us negative 1. Variable part stays the same. We've subtracted the coefficients. What if we do negative 6a plus 3a? What are we going to end up with here? What do you think, Aaron? What? Just that? You've got to have that a on there. That variable part's got to stay the same. And what do we do with our 2? Our poor, sad little 2. It just stays alone. Nothing to combine with. Okay? Now, we usually don't write, if we have a coefficient of 1 or negative 1, we usually don't actually write it down. It's not incorrect, but we usually don't write it. So this we would probably write as negative a squared minus 3a plus 2. Okay. Okay, the last example here. You guys should be good enough now that you can probably tell me how to do this one. Okay? What am I going to do first? Gabrielle, what should I do first? Find my things. What do we call these things that we find?
Like terms.
Absolutely. So is there anything in here that is a like term with 3x squared? Okay. And I'm going to include the negative sign with it to make it negative 2x squared. Is there anything else?
X squared.
Yeah, the negative x squared is part of it too. Okay. Are there any other like terms in there? Liam? Okay. And? Okay. And once again, we have a sad little xy term left at the end. Okay, I'm going to rearrange this now to put my like terms next to each other. And when we say collecting like terms, this is what we mean by collecting like terms, is moving these terms together so that they're next to each other, like terms. So 3x squared, I'm going to move the negative 2x squared, and I'm going to move the negative x squared, so they're all next to each other. Then I'm going to have my plus 7y, my plus 5y, and my plus xy. Okay. So we've got all of these like terms that are right next to each other. Okay. And then what did I use? I used the squiggle there. Just that. Okay. So what's our next step? We want to combine these things together. First off, we have three things. This isn't a problem. We just add or subtract all three of the coefficients as appropriate. So what are we going to have for that first one there? We're going to have 3 minus 2 minus 1. What does that give us as a coefficient? 0. Okay, that's a little bit weird. What's our next one going to be here on our y's? Yeah. And then finish it off for us. Plus the xy. Okay. When we get this coefficient of 0, this is like 0 times x squared. So if we take anything and we multiply it by 0, what's the answer? 0 times 5 is 0 times 10 is 0 times 2 billion is 0 times 3 billion is, yeah. So this is just going to be 0 no matter what we do. So if it's 0, we don't even write it. And we would just write this as 12y plus xy, and that would be our final answer. And that is collecting like terms. Okay.